Hello and welcome back to the video lecture series on statistics for machine learning. I'm Amit Kumar Das and we are going through the very important topic of sampling the distributions and all. Now, we just looked at the central limit theorem, which is a very important theorem in context of the sampling theory, right? What does it say? We have already seen that if we draw a random sample of considerable size, and that considerable size is being mentioned as greater than equal to 30. So the sample size greater than equal to 30, then the sampling distribution of the sample mean follows a normal distribution with uh, the value of mean is equal to the x bar, and the value of the standard deviation is equal to standard error of x bar. Okay, so this is what the central limit theorem states. Now, one thing we also need to know is standard error of x bar. There is a relation with the population standard deviation. Okay, so we need to understand that the relation between the standard deviation, or rather standard error for x bar, and the population standard deviation, mind it. So I would rather not mention this one as mu. Let me just and this one as sigma, because that will become confusing with the population values. So let me just write it as mean for the sampling distribution of x bar, and let me write this as standard deviation for the sampling distribution of x bar. So mean for the sampling distribution of x bar is equal to the x bar itself, and standard deviation for the sampling distribution of x bar is equal to uh, the standard error of x bar. Okay, now when we talk about the relation between the standard error of x bar and the population standard deviation, the relation goes like this. So standard error is equal to sigma, which is the population standard deviation, divided by root over of n. Okay, sigma by root over of n. Now, say I have a standard deviation for the population as, say, 20. Okay, I'm just hooking up some number, and let me say that the sample size, say for example, is 900. Okay, or say 400. Okay, so 400. So root over of 400. So this is going to be 20 by 20. Okay, so 20 by 20, which is equal to 1. This is going to be the value of my standard error. This is very important to note. Okay, and we'll now look at a couple of problems to help us understand how the calculations need to be done. Okay, so the problem goes like this. Say I have a normal population with a mean of 0.1, okay, and a standard deviation of 2.1. So basically, this is the value of mu. Okay, the mu value is 2.1, and the standard deviation, so sigma value is basically, sorry, mu value is 0.1. So mu is equal to 0.1, and sigma, which is the population standard deviation, is equal to 2.1. Find the probability that mean of a sample of size 900 is negative. So I draw a sample of size 900. So n is equal to 900, right? Find the probability. So what is the probability that the mean of that sample which is being drawn is negative? So I have got mu is equal to 0.1, sigma is 2.1, and sample size is 900. Okay, one more thing which is given is the value of z. Remember that standard normal variable or standard normal variate, that value of a specific value of that is being given in the problem. Okay, and that is basically the p of z modulo is less than 1.43 is equal to 0.847. We need to interpret that one first, okay, so that we have a very clear perspective. So this is the standard normal curve. We have seen that, and the values for mod z, mod of z less than 1.43. So this is the, say, z is equal to minus 1.43. Okay, this is minus 1.43, and we have another one here. We have z is equal to 1.43. We have two sides on here. Okay, and it is being told that mod z less than 1.43 is equal to 0.847. So what does it mean? It means that the area under the curve between minus 1.43 and plus 1.43. So within this area, the area is 0.847. Okay, and we also know that if this one is like z is equal to 0, this is z is equal to 0. Okay, that is a mean. So here, obviously, on each side we have 0.5 and 0.5. Both sides of the curve are 0.5. This side also 0.5 and this side also 0.5. The whole thing. I mean the whole thing, this whole area. Okay. So now we have to find out. Okay. Now, standard deviation for the population, and it's a normal population. So we can apply the central limit theorem here. So for the central limit theorem, I mean, using the central limit theorem, we can say that the sample size, so sampling distribution of sample mean, we can figure out, right? Sampling distribution of the sample mean. So sampling distribution for the sample mean will have a mean of, mean is equal to the population mean, right? So the mean of the distribution is going to be mean x bar is equal to mu is equal to 0.1. Okay, and the standard deviation, so sigma is equal to, or rather not sigma, I should not say sigma because that is going to be confusing. So standard deviation is going to be the standard error of the sampling distribution of x bar, which is again I have seen is equal to 0 by root over sigma by root over of n, where sigma is the population standard deviation. So 2.1 divided by root over of 900. Okay, so 2.1 divided by root over of 900, which is going to be 2.1 divided by 30. So 2.1 divided by 30 means 0.7 divided by 30 divided by 10. So 0.07. This is going to be the value. Now, let me just extend it a bit. Okay. Now, the thing is, I have to find out the probability that the mean of a sample of this size. So the mean, so I have to find the probability. So probability, one second. So probability, what is happening? P of x bar less than 0. Probability is negative, right? We have to find the probability that x bar is negative. That's a mean. Okay, so that is going to be P of, now if I convert this to z variate, what is it going to be? Z less than what? So less than 0 minus the mean. So 0.1. Okay, divided by what? Divided by the standard deviation. So what is the standard deviation? 0.07. Right, this is my standard deviation. So this is what I have. Now if I do the maths for this one, it's going to be negative. So this is equal to P z less than minus, so 0.1 divided by 0.07. What is the value going to be? Let me just divide it. So 0.1 divided by 0.07 is equal to 1.43, right? This is going to be 1.43. So 1.43, right? This is 1.43. This is what I have to find out. Now, if I just think in context of this curve, so what is the thing that I'm trying to figure out? I'm trying to figure out this particular area, right? This area where this is z is equal to minus 1.43. This is minus 1.43. This particular ordinate, okay? And I'm trying to find out the area to the left order of the ordinate because I'm trying to find out z less than minus 1.43, right? So what will be the value be? So sorry, so this is going to be is equal to, so the whole area is 0.5 to the left of z is equal to 0, so this is 0.5, okay, minus this small area. What is this small area? So 0.847, sorry, minus this larger area, because if I take this half of the bell shape and I subtract this portion, then I'm going to get this portion, right? And this is 0.847 divided by 2. So 0.847, right? 847 divided by 2. Okay, so what is the value going to be? 0.847. What is the value of 0.4847 divided by 2? 0.847 divided by 2. What is it? 0.4235. And if I just subtract minus 0.5, so 0.0765. So my answer will be 0.0765, right? This is the probability of the value of the mean for this sample, this random sample being drawn, random sample of size 900 being drawn is negative. This is my whole workout. Okay, so this is how we can solve a problem. Though for machine learning, we don't need to break our head with such complex problems, but I just wanted to show you quickly how we can work out problems using the central limit theorem, where we can either use the population mean and calculate the sample mean, or vice versa, right? So either the value of the statistic from the I mean not statistic, the this thing from the population mean, if I want to calculate the mean of the sampling distribution. That's how we can do it. Okay, so we'll come back with more such concepts. So stay tuned. Thank you very much.